In a given population, the proportion who have a certain characteristic is called the population proportion. In a simple random sample of n individuals, let x be the number of individuals in the sample who have the characteristic we're looking for. Then we define the sample proportion, written here as p with above it a hat, so p hat, is defined to be x, the number of individuals that had the characteristic, divided by n, the number of individuals sampled. Now a little bit of notation, the population proportion is just denoted by p, so that's in the entire population how many people have the characteristic we're looking for, or the proportion of that, versus the sampled proportion, which is our p hat. As we can't necessarily look at the entire population and see who has our characteristic we're interested in, instead we choose a simple random sample, a smaller group, and of that group we see who has a characteristic, and that is our sample proportion. Now this brings us to the central limit theorem for proportions. Let p hat be the sample proportion for a sample size n and a population proportion p. The key phrase here is if this condition and this condition is met, then the distribution of p hat is approximately normal. Once we know the distribution is normal, we can find the z-score, and then from the z-score we can use our cumulative normal distribution table to figure out the probabilities that we would lie below a certain value, above a certain value, or between two values. And in order to find the z-score, we know the z-score formula is in general the item minus the mean over the standard deviation. But since we're dealing with our sample proportion, we have specific means, mu sub p hat, and specific standard deviation, sigma sub p hat. So once we know we're in this sample proportion idea, we'll calculate the z-scores after we find the mean and the standard deviation as our data value minus mu sub p hat divided by sigma sub p hat. So keep these formulas, both what we need to check to see if it's approximately normal, and then once we've checked it, the formula for mu sub p hat and sigma sub p hat close at hand as we go through the next problems. So our standard procedure for these type of problems is to first check and make sure the two conditions are met, and if they're met, then we use the formulas above to find mu sub p hat and sigma sub p hat. Then from that, if we need to, we can find our z-score. Next, we can make a sketch of what we're looking for in our normal curve, shade what we're looking for, and then finally use the cumulative normal distribution chart as we've done in the previous few lessons. So our next example reads, it's reported that 5% of people who receive kidney transplants were under the age of 18. So that is a percentage based on our entire population. So we can turn this into our population proportion. P, 5% is 5 out of 100, which will turn into the decimal 0.005. How large of a sample of kidney transplant patients do we need to draw so that our sample proportion, p hat, is approximately normal? And this comes back to what we wrote here. If this condition is met and this condition is met, then the distribution of p hat is approximately normal. So we need to set up these two and verify what n would make this true. So I've got n times my p of 0.05 needs to be greater than or equal to 10. I can solve that equation. N times 1 minus 0.05 needs to be greater than or equal to 10. I'll solve that equation. So we know our value of p found above. So I'm going to write n times 0.05 needs to be greater than or equal to 10. Now here I can solve. I want to get n by itself. It's currently being multiplied by 0.05. So I'll just divide both sides by 0.05. Type that into the calculator, and from this one we see n needs to be greater than or equal to 200. And as we solve the next one, we still don't know what n is, but we have 1 minus our value of p. And I'm going to clean that up before we solve it. 1 minus 0.05 is 0.95, so n times 0.95 times our value of that. Now I'll divide both sides by 0.095. Algebraically isolating n, and we see from this, n should be, when we type it in the calculator, greater than or equal to about 10.53 when rounded. So we've got two values of n. To make the first inequality true, it has to be greater than or equal to 200. To make the second inequality true, it has to be greater than or equal to 10.53. But notice we need both inequalities to be true. So we're going to pick the largest of the two criteria. So we're specifically interested in when n is greater than or equal to 200, because if n is greater than or equal to 200, it is also at the same time greater than or equal to 10.53. So in this way we'll meet both conditions, and we can conclude by saying that we'll need a sample of at least 200 in order for the sample proportion to be normally distributed. So the last example was trying to figure out, if we know the population proportion, how large of a sample do we need to draw to ensure that our sample proportion is normally distributed? So that's kind of the setup phase of our sample. In this next example, though, we are given that it is reported 63% of U.S. adults drink coffee daily. A random sample of 250 adults is selected, so we've already got our sample selected from here. Now let's take a moment. What do you think you would translate this to? The 63% who would drink coffee. What would you translate this 250 to in terms of our notation from the previous page? Well, 63% is a proportion of the entire population. That's our population proportion. So that's P is 63 out of 100, or 0.63. And 250 is the number in our sample. That's our N value. N is 250. So as you read through these problems, try to translate back into the notation of the problem. Now we're asked to find the mean, mu sub p hat, so the mean for this sample proportion. And if you look back on the last page, the formula says mu sub p hat is just equal to p. So in this case, we can just record it 0.63. Next up, standard deviation, sigma sub p hat. We have the formula that we'll write down here. And let's say that we will, just as a matter of course, round to 4 or 5 decimal places in our problems unless otherwise stated. Maybe let's say 5 to increase accuracy, round to 5 decimal places. Now we'll set this up and then type it into the calculator. We've got the square root of our p-value is 0.63, which is then multiplied by 1 minus 0.63, which is all divided by our value of n, which is 250. So here I'm first going to calculate 1 minus 0.63, multiply that by a 0.63, and now I've got the top part of my fraction. Divide it by 250. Then I'll take the square root, and we get about 0.03053, which right past the 3 is a 5, so if we're rounding to this decimal place, we'll round that to 4. So next we're asked, find the probability that more than 67% of the sampled adults drink coffee daily. Now we know it's reported 63% of the population drink coffee daily, but we're trying to figure out what's the likelihood that 67% of our sampled adults, so that sample of 250 that we draw, drink coffee daily. So this is now, if I translate the 67%, if it's a percentage, always translate it to a decimal. That's 0.67. That's kind of my new data value. That's what I'm looking for. What's the likelihood that we're more than this value? Well, in order to do that, I would need to have a normal distribution that I could calculate a z-score for, that I could go to our cumulative normal chart. But before I can assume this is normal, I need to check our two conditions from before. For my value of n and p is n times p greater than 10, and is n times 1 minus p greater than or equal to 10. If both these are true, I can assume it's normal and then go about the rest of the problem. Let's check those now. So I've got n times p. I know that needs to be greater than or equal to 10. Now my n value is 250 from above. P is 0.63. Let's see what this actually is. And we get 157.5. That's definitely greater than 10, so that one's good. Next one is n times 1 minus p. So let's see, 1 minus my p-value of 0.63 is that times 250. That's 92.5, which again, it just had to be greater than or equal to 10. So we meet that, so we're approximately normal. Now it just so happens in part A and B of this problem, we already found our mu sub p hat and our sigma sub p hat, so we don't have to find that again, but I'll record it here so that we can see it clearly. And if a future problem didn't set it up so nicely for us, we would at this point find mu sub p hat and sigma sub p hat. Now that we have these, we can go to our z-score. We know the z-score is the value that we're interested in, 0.67, minus the mean of the population sample, which is our 0.63, divided by 0.03054. We'll calculate that. And we know our z-scores, we round to 2 decimal places. So we've got our 0.67 minus 0.63, divide that 0.03054, and we see that rounds to 2 decimal places to be 1.31. Now we know when we look at the chart will give you the amount that comes before the z-score. So that will give you the probability that the sampled adults of the sampled adults, 67% or less drink coffee daily. But we're interested in the more than, so we know once we find this value from the chart, we then need to say, well, the part that we're actually looking for is the more than that, which is 1 minus that value. So now let's go to our chart and find what is the area before the z-score of 1.31. So looking at the z-score, the cumulative normal chart, we find our z-score of 1.3 row with the column of 0.01. That's the amount of area contained before that value. We'll record that on our paper. So the amount of the curve that we're actually looking for is the part that's greater than that. The entire curve is 1, so what we're looking for here that I'm shading now in red is 1 minus the value we found, which will give us 0.0951. Now as we read through the next problem, it says find the probability that the proportion of sampled adults who drink coffee daily is between 0.6 and 0.7. Since we've already done part C, we have verified that our sample proportion distribution is normal. So I don't have to do that again for this same problem. However, if it hadn't already been done, you always need to verify first, is n times p greater than or equal to 10? Is n times 1 minus p greater than or equal to 10? So we've done that. So now we've also already got our mean of p hat and our standard deviation of p hat from before. So we don't have to recalculate that. Now all we have to do is find our 2 z-scores, and we know how do you deal with between if it's normally distributed. You find the area that goes before the larger number from the chart, find the area that goes before the smaller number from the chart, and then take larger area minus smaller. It's the same procedure as before. We're just applying it to this new situation where we have our sample proportion. I'd encourage you to pause the video now, find the z-score for 0.6, find the z-score for 0.7, and then find their corresponding areas before 0.6 z-score, area before 0.7 z-score, and then unpause and we'll check our work to that point together. So when I calculate both of these, I get the z-score for 0.6 is negative 0.98, the z-score for 0.7 is 2.29 when rounded to 2 decimal places. Now I'm going to draw from the chart, I'm going to get the area before both of these, so I'm going to indicate that here. So because of how the chart works, I know I'll get the area that lies before negative 0.98 if I look up this z-score in the chart. I know I'll get the area that lies before 2.29 if I look up 2.29 in the chart. And then once I have the two areas, I'm going to take the bigger area, which overestimates it, and then subtract by the exact amount it overestimates it, the area found here. And with that, I'll get exactly the amount between our 0.6 and 0.7. So now let's go to our cumulative normal distribution chart. So for our negative 0.98, I find the row for negative 0.9, the column for 0.08, see where they intersect, and that is 0.1635. We'll record that. Similarly, let's look up the value for 2.29. And when we see where the 2.2 row crosses the 0.09 column, we get 0.9890. And our final step in this type of problem for the between is to take the larger area minus the smaller, and we get our likelihood that the proportion of sampled adults who drink coffee daily is between 0.6 and 0.7 to be 0.8255. Now our final question is, would it be unusual if less than 57% of the sampled adults drink coffee daily? We know the question of if it's unusual means that we need to find the actual likelihood that it'd be less than 57%. And if that's less than 0.05, then it is unusual. If it's greater than 0.05, it's not unusual. So that's our cutoff for is it unusual. To do this, we need to go through, and we can't answer this question unless it's normal. But as this is part of a previous problem where we already showed it's normal, we don't have to recalculate that. Similarly, since it's part of the previous subparts, we don't have to recalculate the mean for the p-hat or the standard deviation for the p-hat. We can just copy that down again. Now we are going to find our new z-score because now our cutoff we're interested in is 57%, which we know we write as 0.57. So my z-score is 0.57 minus the mean of 0.63 divided by my standard deviation of 0.03054. Type that into the calculator. You know z-scores always round to 2 decimals. And we see we should round this to negative 1.96 as our z-score. Now we know the chart will always give you the area to the left, so that's the values less than, which if we read the wording, that's exactly what we're looking for. So from the chart, I'll be able to get my area. Once I have my area, I'll be able to say, is it less than the 0.05? If so, it's unusual. If not, it's not unusual. So we'll go to our cumulative normal distribution chart, find the row for negative 1.9, the column for 0.06, see that they intersect at 0.0250, and then we'll make our conclusion 0.0250 is distinctly less than 0.05. So this would be an unusual case if less than 57% of the sampled adults drink coffee daily. So in our next example, it says high blood pressure has been identified as a risk factor for heart attacks and strokes. It is reported that the proportion of U.S. adults with high blood pressure is 0.3. So as we read through, we realize this is our population proportion. 0.3 is our p-value. Now, of the entire U.S. population of adults, we drew a sample initially in 38. Now, Part A asks, is it appropriate to use a normal approximation to find the probability that more than 40% of the people in the sample have high blood pressure? If so, find that probability. If not, explain why not. So the first thing is we need to answer the initial question of, is it appropriate to use a normal distribution? And that will be if n times p is greater than or equal to 10, and if n times 1 minus p is greater than or equal to 10. So let's check both of these conditions. So our is it appropriate we'll answer here. N is 38 times a p-value of 0.3. That will be equal to 11.4, which is greater than or equal to 10. All we have to do is be greater than or equal to. Next, we'll check the second condition, our 38 times 1 minus p. That will be equal to 26.6, which is greater than or equal to 10. So both conditions are met. So our first answer is it is appropriate to use the normal approximation. Now, once we know we can use our normal approximation, what we're doing here is we are trying to look at our sample. So we need to know our mean of the sample and our standard deviation of the sample. That will go back to our two formulas. Mean of the sample, mean of p hat is p. Sigma of p hat is the square root of p times 1 minus p over n. And we know when it comes to calculating the standard deviation of p hat, we'll round to about 5 decimal places. So here our p was said to be 0.3, and now we'll begin to calculate this, the square root of 0.3 times 1 minus 0.3 over our sample of 38. And we'll round that to 5 decimal places, and we get 0.07434. Now we're interested in the likelihood, the probability that more than 40%. So our 40%, this is going to be our x of 0.4. So now that it's normal, I know I can find the z-score attached to that. The chart will then give me the probability that I'm less than 40%, but then I can just do 1 minus that value and we'll get the amount, the probability that I'd be more than 40%. So we'll begin with the z-score here. My z-score is 0.4 minus my mean of 0.3 divided by my standard deviation. We know we round that to 2 decimal places, and that will round to 1.35 as a z-score. I'm going to draw my chart just because it's visually helpful, not necessary if you know the procedure. So we look at the chart for the z-score of 1.35, and we get 0.9115. Now that would give you the probability that less than 40% of the sample have high blood pressure. We wanted more than, so I find that by saying it's 1 minus that amount. And that will be 0.0885. Now in problem B, it kind of restarts the problem because it tells us a new sample of 80 adults is drawn. This is going to change my n-value. And when the n-values change, that's going to change if it's normal. It won't change your mean because that's still going to be our 0.3, but it will change my standard deviation for the sample proportion because you have to divide by n to find the sample deviation, standard deviation. So let's just quickly verify it's normal. I mean, we could just think through it. If it was normal at 38, then by drawing a bigger sample, it should still be normal. But we can quickly go through the calculations to verify. The same p-value of 0.3 from before times our new population of 0.8, that will give us 24, which is definitely greater than or equal to 10. The first one's met. The next one, our value of 80 times 1 minus 0.3. We'll get 56, which again is greater than or equal to 10, so we know it's normal. Now we need to find our mu of the sample. So mu sub p hat is just the population proportion of 0.3, that's unchanged. However, our standard deviation of the sample will now change because it's dependent on n, and our new n value has changed. So it's 0.3 times 1 minus 0.3 because it's p times 1 minus p over our new sample value of 80. We'll type this into the calculator and round to 5 decimal places. And we get 0.05123. Now we needed these two so that we could then calculate the z-score that corresponds to 40% of the people in the sample having high blood pressure. So that z-score will be, turn that into a decimal, 0.4. 0.4 minus the mean of 0.3 divided by our standard deviation. Round that to 2 decimal places. And we get that rounds to 1.95. We know the chart will give you the probability that you're less than that value. We in the end want more than that, so I'm going to mentally say whatever number I get, I'm going to do 1 minus that to get my final answer. We'll go to the chart now to find the area that lies before the 1.95. The row of 1.9, the column of 0.05, and we get 0.9744. That would be the probability that less than 40% of the sample have high blood pressure. To find what we're actually looking for, we want to find more than that, so it's the total minus what we don't want, so 1 minus this value, which will give us 0.0256. So for part C, it says find the probability that less than 25% of people in the sample of 80 have high blood pressure. Now just based on the wording, can you visualize, are we going to use this mean and this standard deviation, which I've just circled, or this mean and this standard deviation, which I've boxed? As it said the sample of 80, we're going to have to go with the mean and standard deviation that came from the value of 80. So this is another encouragement. As you work through, especially these multi-step problems, be sure you're writing it out just like you're seeing me write things out on the screen. You should have a blank piece of paper, label your work, because if I didn't correctly write all this down, I would have to recalculate the mu p hat and the sigma p hat. But now that I've got it clearly recorded, I know the mu is 0.3, I know sigma is 0.05123. So have well-structured work. Now we're looking at the probability that it's less than 25%. At this point in the video, we've done problems like this multiple times. I would encourage you now to pause the video and attempt this entire problem on your own, and then unpause to check your work. Remember, these are ways that you can check your understanding and then unpause and get immediate feedback if it was correct or incorrect. So pause the video now, attempt on your own. unpause to check your work. Now the first thing I have to consider is it normal? But as this is based on something that I've already calculated in B, I know the normal distribution applies, and I know the mean and the standard deviation. So I don't have to recalculate that. That's going to save me a bit of time here. Now I just need to find the z-score that corresponds to this. We know 25% turns to 0.25, so my z-score is 0.25 minus the mean of 0.3 divided by the standard deviation of 0.05123, rounded to 2 decimal places as always. And this will round to negative 0.98. Now I'm going to draw this just to help me visualize. It's not necessary if you know kind of the verbal cue, since it's less than, it's straight from the chart. Greater than, remember, is 1 minus what the chart says. Between is chart of the larger minus chart of the smaller. But here I've got my negative. It's before, remember, 0 is at the highest point, so negative should be to the left of it. I know the chart will give me what's less than that, which matches exactly the wording of the problem. So let's look this up in the chart. So we see that would give us a value of 0.61635. And that would be our answer to this question. So look over your work, see did you get it correct when you attempted on your own? If not, see to what point were you on the same page as me? And then at the point that it differed, what was different on your page and how could you correct that based on what you now see on the screen? So that'll be it for this lesson. As always, if you have questions, feel free to reach out to me via our campus communication and I'll be happy to answer your questions.